Hello everyone, welcome to the e-learning program of KTGM College Nasik. Dear students, in the previous lecture, we have seen about the interaction of the light with matter, population density and the Boltzmann distribution law. Students, in today's lecture we are going to see about the Einstein's coefficient and the relation between these Einstein's coefficients, which are known as the Einstein's relations. Students, in the previous two lectures we have seen in details about the energy level diagram, the interaction of the radiation with the matter, and the three processes related with the lasing action, such as the absorption, spontaneous emission and the stimulated emission. On the thermodynamic ground, the Einstein postulated that the probability for spontaneous emission is related to the probability of the stimulated emission, and the relation between them is calculated from the quantum mechanics. Now that means, with the help of the quantum mechanics, Einstein put up some relations between the probability of the spontaneous emission and the probability of the stimulated emission, and these relations are known as the Einstein's relations. The Einstein coefficients are simply the mathematical quantities which are measures of the probability of the absorption or the emission of the light by the atoms or the molecules. Now, to obtain the Einstein coefficients and the relation between the Einstein coefficients, now we have to be considered the two-level system. Now in this diagram we can see the two-level energy diagram. Now let these levels are denoted by the energy, say as the E1 for the ground state energy for the lower level and the energy E2 for the higher level, and the population of these two energy levels, say as the N1 and N2 respectively. In the previous lectures we have seen, when the atoms are subjected to an external light of the frequency nu, when incident on the atoms, then the three processes may be occur in that medium, such as the absorption of the radiation, spontaneous emission and the stimulated emission. Students, now here again we are going to see in details about the three processes, what happens in these three processes, and with the help of these three processes how we can obtain the relation between the Einstein coefficients. Now first is the absorption of the radiation. We know that the absorption of the radiation is the process by which the atoms in the ground state absorb the energy from the incident photons and jump into the higher energy level. Now this process described by the Einstein coefficient, which is the B1. So now in this diagram we can see here. Now this is the incident radiations having the energy equal to the h nu, when it incident on the atoms which is in the ground state, now then these atoms absorb the energy and it goes to the excited energy level. That means you can say that higher energy levels. Then the number of the atoms per unit volume that makes of the upward transition from the lower level to the upper level per second is called the rate of the absorption transition. Now that means when the photon which is when the atoms which is in the ground state when absorb the energy, then it goes to the higher energy level. That means it makes the upward transition from lower energy level to the upper energy level, and that transition rate is nothing. That transition rate per second is called the rate of the absorption transition, and the rate of absorption transition is given by the RABS is equal to minus the derivative of the number of the atoms which is in the ground state with respect to the time, that is minus dN1 by dt. Now here the negative sign indicates that there is the decrease of the population at the lower energy level given. That means during the transition the number of the atoms goes from the lower energy level to the upper energy level. Now that times there is the decrease in the population in the lower energy level. The rate of absorption transition occurring in the material at any instant will be proportional to the number of the atoms per unit volume. In the lower energy level, that is, we can say that the population N1 and the number of the photons per unit volume in the incident beam, that is nothing but the density of the incident beam. So we can write here the rate of absorption transition is directly proportional to the population in the lower energy level N1, lower energy level which is at N1, and the density of the beam, that is rho nu. Now here rho is the function of the nu here. Therefore we can write here the minus dN1 by dt is equal to be the B12 into the rho nu into the N1. Now here this B12 is the constant of the proportionality and which is known as the Einstein coefficient of the induced absorption, and it gives the probability and it represents the probability of the absorption of the radiation from the level 1 to the 2. That means Einstein considered this proportionality constant is nothing but the probability of the absorption radiation from the lower energy level to the upper energy level. Now then we can write here in terms of the Einstein coefficient of the induced absorption, which is equal to be the minus dN1 by dt divided by the rho of nu into the N1. The second process is the spontaneous emission. Now we have seen that the spontaneous emission is the process by which the atoms in the excited state return to the ground state by emitting the photons. We know that the lifetime of the excited atoms in the upper energy level or in the excited state, which is equal to be nearly 10 raised to minus 8 seconds. After that it comes to the lower energy level, and during that process or during this transition it emits the radiation, and such a process or that process is known as the spontaneous emission. Now this process is described by the Einstein's coefficients, which is known as the A21. So now in this figure we can see here, now here that is before the photo emission, and in this figure we can see that the photo emission during this transition. So when the atoms goes from the higher energy level to the lower energy level, that times it emits the radiation, and that radiations are known as the spontaneous emissions, or that process is known as the spontaneous emission, and which is denoted by the Einstein coefficient, that is A21. Now in this process, the rate of the spontaneous transition, which is given as the R spontaneous is equal to the minus dN2 divided by the dt. Now that means here the negative sign again indicates that here there is the decrease in the population at the higher energy level during the transition. Or in another way we can write the rate of the spontaneous transition is equal to the dN1 by dt. Now that means there is the increase in the population in the lower energy level. So remember here the difference between how to write in terms of the negative sign and the positive sign. The rate of, now in case of the spontaneous emission also, the rate of the spontaneous transition at any instant will be proportional to the population of the excited state only. Now here we have already considered the population of the excited state is N2. Therefore we can write the dN1 by dt is directly proportional to the N2. Therefore the rate of the spontaneous transition is equal to the A21 into the N2. Now here the A21 is the proportionality constant, and which is known as the Einstein coefficient of the spontaneous emission, and it represents the probability of the spontaneous transition from the level 2 to the 1. So the students, you have to be remember here what the Einstein coefficient indicates here. So the A21 is the coefficient of the spontaneous emission, and it represents the probability of the spontaneous transition from level 2 to the level 1. So we can write, or we can define, the rate of the spontaneous emission is equal to be, or expressed in terms of here, the dN1 by dt divided by the N2. The third process is the stimulated emission. We have already explained about the stimulated, I have already explained about the stimulated emission, that in this process, the stimulated emission is the process by which the incident photon interact with the excited atoms at the excited state and forces it to the ground state. Now that means if the incident photons will interact with the atoms which are in the ground state, which are in the excited state, then there is the transition from the excited state to the lower energy state, that is the ground state, and such a type during that there is the emission of the radiation, and such emission of that the radiation is known as the stimulated emission. So now in this figure we can see here that now this is the atoms which is in the excited state. When it interacts with the incident radiation, now then the forcefully, now the atoms will goes from the excited state to the lower energy state, and during that there is the emission of that the radiation, and such a type of the emission is known as the stimulated emission. So in stimulated emission, the light energy is supplied directly to the excited electron instead of supplying the light energy to the ground state here. And this process is described by the Einstein coefficient, that is Einstein coefficient, that is B21. Now here is the B21. We can the Einstein also express that Einstein coefficient of the stimulated emission in terms of the rate of the transition, and the rate of the stimulated emission of the photons at any instant will be proportional to the number of the atoms per unit volume in the excited state, that is the population density of the higher energy level N2, and the number of the photons per unit volume in the incident beam, that is density of the incident beam. Therefore we can write here that is the rate of the stimulated emission is directly proportional to the population density of the excited state N2 and the density of the incident beam, that is the rho of nu. Therefore we can write here the dN1 by dt is equal to the B21 into the rho of nu into the N2. Now here this B21 is the constant of the proportionality and is known as the Einstein coefficient of the stimulated emission, and it represents the probability of the stimulated emission from the level 2 to the 1. So the students, again here you have to be remember that the Einstein coefficient of the stimulated emission B21 is represent the probability of the stimulated emission when there is the transition from the higher energy level E2 to the lower energy level E1. Now then we are going to obtain the Einstein's relations here. Now under the thermal equilibrium, the net change in the number of the any excited atom is 0. That means the number of the atoms goes from the lower energy level to the higher energy level must be equal to the number of the atoms goes from the higher energy level to the lower energy level. And these conditions requires that the number of the transition from E2 to the E1 must be equal to the number of the transition from E1 to E2. That is, we can say that the